Ah, welcome. Welcome back, everybody. I just want you to know, because you all personally care about how I went ahead to make this, I did this whole presentation once and found out that the audio didn't record. So this is, in essence, the life of being a teacher, in that you will say the same presentation multiple times in the course of one day, hopefully getting all your students to understand. I know you guys have been troopers through this. I know it's been a hard time so far, and I want you to know I see the work that you're doing. I see the questions you send me, and I appreciate all that you do. It's a weird time we're in right now, and I don't want to stop your educational pursuits simply because of it. So, here, I've heard a lot of your feedback. A lot of people pretty much said they need more direct instruction on how to do this beyond what the websites say. And I hear you. So I got you. So here we go. I made a presentation, and we're going to go through this together. Friction and free body diagrams. Just to recap, a free body diagram is a picture of an object that shows all forces acting on it. This is an example of a free body diagram right here. The box with the arrows coming out of all sides. You may remember from some of the websites that we saw, and maybe some of the notes from before our break, that each arrow here would have a very specific type of label, a type of force. We're going to get into that in just a sec. But here's the general picture of a free body diagram. It's the object with all the forces acting on it. There are four main forces that act on objects, and we took these notes before we left. So if you were absent, maybe this is brand new to you. If you were there, this should be a review. If you were absent, but that's all the videos I posted, this should still be a review. Whatever, here they are. Force of gravity. It's the pull of gravity on an object. Normal force. The support force that acts perpendicular to the surface. Essentially, if the object is touching a surface, there is a normal force. Friction. It's the force that opposes motion, caused by the direct contact of two objects. Friction always opposes motion, whereas gravity is always down. There is never a set direction for friction. And lastly, external push. Now, in some of the websites, it called it an applied force. Wow, my handwriting is just as bad on the computer as it is on the board. On some of the websites, they would call external push applied force. Just so you know, they mean the same thing to me. I learned it as external push. If you ever see FAPP for applied force, it means the exact same thing. It's essentially anything that's just added to the situation. Now, let's examine this situation. What would be the free body diagram of a 5-kilogram crate sitting still on the ground? All right, well, this is what I'm going to do. I'm going to go ahead and put the mass of 5 kg right smack dab in the middle of the crate, just so I know what the object's mass is. I don't want to confuse that. The 5 kilograms is a mass, it's not a force. Therefore, it won't be one of the arrows on the free body diagram. But there you go. What forces are currently acting on this? Well, I don't know. It just says it's sitting on the ground. How am I supposed to know that? Well, we could generally assume that all these problems are going to take place on planet Earth. If you're on Earth, you will have gravity. So that's why it says F of G, yes. This chart here is a kind of a notation of all the forces. So if you're starting a problem and you don't know what forces to put, maybe you want to go through individually and see, hey, is gravity acting on it? Is there a normal force? So on and so forth. Well, is there a normal force? Well, if this crate is sitting on the ground, is it touching a surface? Yes, it's touching the ground. We got a normal force. Is there an external push or an applied force? Well, it doesn't say so, and if the crate's sitting on the ground, it's probably not getting pushed. So I think it's safe to say that no, there is no external push. There is no applied force. It's supposed to be an X. And lastly, is there friction? Well, is there motion? Well, if there's no motion, there's no force to oppose motion. Friction's odd that way. Friction only appears when you try to move. If you don't move, there's no friction. Go figure. Now, great, so we have 2 of the 4 forces. How do I draw them? Where do the numbers come from? Well, we cannot forget FEMA. F equals ma. In order to get the force of gravity, we can take the mass of the object and multiply it by gravity. Force of gravity, this is how you're going to get the F of G. The force of gravity is always going to be the mass times gravity. Because we're on planet Earth, gravity is negative 9.8. When you multiply this out, you get negative 49, but negative simply means down. So the down arrow is 49 newtons. So this arrow is going to be called F of G. That's the force of gravity. And I want you to know that F of G is always going to equal mass times gravity. Always. No exceptions. Every time. The down arrow is always going to be mass times gravity. Great. Well, that's the gravity. What about the normal force? Well, the normal force is the support force that keeps it still on the ground. So if gravity is pulling down 49, well, that means the normal force is holding up 49. Oftentimes, the normal force cancels the gravity if an object is not moving. Again, if the normal force was ever bigger than the gravity, well, that means the object would be accelerating upward. And that would be a situation like bouncing. If you bounce a ball, it hits the ground and then it goes up. At that point in time, the normal force is more than the gravity, and so on and so forth. If ever the gravity is more than the normal force, well, then the object is like falling through the table or falling through the floor. But right now, when you have balance, there's no motion. There you go. This is the free body diagram, because we have the gravity and we have the normal force. Now, taking the same situation, we still have the 5 kilogram crate. So I'm going to put the 5 kg right there. Still got it. And now it's pushed to the right 10. Okay, so do we still have gravity? Yes. We still have normal force? Yes. Do we still have a push? Well, now we have a push. Yes. Now, for simplicity, I just want to introduce these forces one at a time. I don't say there's friction. Let's assume it's frictionless. Not very realistic, but for, hey, right now, let's just assume there's no friction because I didn't say there was friction. So how's this one going to look? How is this free body diagram going to look? We have 3 forces, so that means we have 3 arrows. That arrow is the F of G. Mass times gravity. Exact same mass as the last situation. This is the normal force, F of N. The normal force cancels the gravity. So the force of gravity is pulling down, and the normal force is holding it up, just like the last situation. Now, the only difference between this situation and the last situation is the fact that there is now an external push, or an applied force. And because it says right 10, we're just going to put an arrow right 10. That's it. That's how you get the free body diagram. We have 3 arrows because we have 3 forces. 3 arrows, 3 forces. Now, friction is the tricky situation where it doesn't have a set direction. Gravity always pulls down, but friction doesn't always go one way. Friction always opposes motion. So you've got to be able to read the situation, understand where the object is going to go ahead and assign the friction appropriately. Now, here we go. This is the good stuff. A free body diagram with friction. So this one's going to have all 4 forces. I'm telling you it has all 4 forces, but how would you know if I didn't tell you? Well, it says, okay, what would be the net force of a 5 kg? Okay, all right, 5 kg. All right, 5 kg. Ah, yes. 5 kg crate that's pushed to the right 20 newtons, but experiences 5 newtons of friction. So I see the push and I see the friction right away. Because it's a crate, I know there's gravity, and it is safe to assume that if you're pushing the crate, it is touching a surface, the floor. I feel like sometimes people are like, well, what if the crate is like hanging in the air? I didn't say it was hanging in the air. I think you could assume the simplest situation. The crate is on the floor and you're pushing it across the room. Okay, so we have all 4 forces. So we're going to see 4 arrows appear around this box. There's the gravity. How'd you do that? Mass times gravity. Don't forget, F of G equals M times G. Normal force still cancels it out. Bazzuto, will the normal force always cancel out the gravity? For now, but not always. You know it's going to get more complicated. But right now, it does. There's the external push, 20. And if you're pushing something to the right, friction must be going to the left. There it is. There's your free body diagram. Gravity, normal, external push, and friction. Nice. So how do you get a net force from this? Let's see. I know that the 49 up and the 49 down cancel. So just like the vectors, you combine your up and downs, you combine your right and lefts, and then you do what you need to do. Just like with the arrows, we might be doing some a squared, b squared, c squaring, but not today. The up is 49, the down is 49. They are the same. The equal and opposite, they cancel. The 20 right and the 5 left, 20 minus 5 is 15. Net force is also written as sigma F, 15, and do not forget the direction. What way is the net force going? It's going right, because the 20 is bigger than the 5. There you go. Let's keep it moving. Okay, so here's another example problem, but this time I'm switching a lot up on you. One, we're no longer having the mass of being 5. Now, the mass is going to be 4. Nice. Do we have the 4 forces? Well, it's pushed and there's friction. It's a crate. We can assume it's on Earth. And it's obviously touching the floor. So we do have the 4 forces. Let's go through this. Got to draw the free body diagram first. We've got to draw the FBD first. So, gravity. Whoa, Pizzuto, where'd that number come from? Don't forget, F of G will always equal mg. Mass times gravity. Mass times gravity. The normal force. For now, the normal force does cancel the gravity. There you go. Okay. The push. Well, now it says it's pushed 40 to the right. Bam. If you're pushing it to the right, that means friction is to the left. Here are the 4 forces acting on the crate. Now, the whole essence behind understanding what a net force is, all these forces are acting on it, but the crate only moves in what direction? What direction does the crate go? The crate goes to the right because the forces in all other directions essentially are either canceled or overwhelmed. The 39.2 are canceled, up and down cancel, and 40 is bigger than 12. Because 40 is bigger than 12, to get the net force, 40 minus 12 is 28 to the right. Acceleration is the net force divided by the mass. This. And are we done? Oh, what direction is it going? It's going to the right. Sorry, I wrote over the answer. I think you can do this one on your own. I know you have your calculators out. You're eagerly calculating this out because you have the 12 kilogram crate. So the 12 kg goes right smack dab in the middle of this box. 12 kg. Oh, nice. It's good handwriting. It's pushed left and experiences friction. Oh, it's a couple things different. I'm going to tell you, you have the 4 forces. Let's take a look. There's gravity. Wait, whoa. Where the heck did that come from? F of G equals mg. F of G equals mg. 12 times negative 9.8. Bam. Normal force cancels that out. Bam. You're pushed left. This time you're pushed left, which means the friction is going right. Ooh, tricky. Friction going right this time. So how does that change things up? Well, the 117s cancel. Gravity normal. Normal, the gravity cancel. We have the push, F of P, and then FR. Okay. 70 minus 10 is 60, but not just 60, it's 60 to the left. Make sure you understand the directionality. The directionality here is really important. Simple. Now, we have done skydiving ad nauseum in this class. We've talked about skydivers many a time before, and I want to just kind of go through this again, because oftentimes I know the question that I'm getting is, when would there not be a normal force? Well, let's think about it. If you go skydiving, let's think about it. Does gravity pull you down as you go skydiving? Sure does. Are you touching a surface when you go skydiving? No. When you go skydiving, there will not be a normal force. Do you have anything else besides gravity pushing you or pulling you down? No, so you don't really have an external push. And do you have friction? Well, actually, air resistance is a form of friction. So when you go skydiving, you have 2 of the 4 forces. Now, let's take a look at this. Little Susie's got a mass of 50 kilograms, and while skydiving, experiences 100 newtons of air resistance. What is her acceleration? So there she is. There's little Susie. All right, math. This time I'm going to put the mass in her head, kind of keep it simple. So we have the 50 kilograms in the head. We have a gravity, and we have a friction. We do not have a push. We do not have a normal. Okay. Well, how do I get the gravity? I cannot stress this enough. Force of gravity will always equal mass times gravity. Always, 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 always. 50 times negative 9.8, bam. Gravity pulls her down, but air resistance is friction. So if gravity's pulling her down, in this case, friction is going to be pushing her up. So air resistance is actually pushing her up. So at this point in time, when she's experiencing 100 newtons of air resistance, that's what her free body diagram looks like. F of G, F of FR. There it is. The net force, just like before, subtract, divide. So skydivers don't actually fall with an acceleration of negative 9.8. Because of air resistance, they don't accelerate as much as if there would be no air resistance. And that makes logical sense. Okay, what about this situation? Little Susie has a mass of 30 kilograms and experiences 294 newtons of air resistance. It's the same thing, you guys. 2 forces, gravity and air resistance. Wait, Pizzuto, hold on. Where did the gravity come from? I wasn't paying attention the last 8 slides. F of G equals mg. 30 times 9.8. Bam. Air resistance. Bam. Okay, so wait a minute. The net force is 0. The 2 airs cancel out. That means the acceleration is 0. Are we saying in this situation that she's not moving? No. What I'm saying is she's actually going so fast that she can't speed up anymore. Don't forget, acceleration means speeding up. So she's going so fast, she can't go any faster. The term for that is called terminal velocity. If you are going so fast and you're hitting so much air resistance that the air resistance could actually cancel the force of gravity, you aren't accelerating anymore. Let's think about what this means, the word terminal. Terminal means ending, ending velocity. If you jump out of a plane, you won't just get faster and faster and faster until you hit the ground. You will speed up until you hit a point where you just can't go any faster because you're hitting so much air that it prevents you from speeding up. You're going so fast, you just can't go faster. Think about it like this. You are driving your car. You put your hand out the car's window. You're driving slowly, you feel a little bit of friction. You drive faster, you feel more friction. Your hand gets pushed back. In theory, there'd be a point where you'd be going so fast where no matter how much you sped up the car, you just couldn't go faster because you'd be hitting so much air. Don't ever try that. That would really hurt your arm. So conceptually, if a heavy person and a light person jumped out of the plane at the same time, we have heavy person, we have light person. Okay? So who has the bigger force of gravity? The heavy person is going to have a bigger F of G because the mass is bigger. Okay? This person is going to have a smaller F of G because the mass is lighter. So as they fall, which person hits terminal velocity first? the lighter person, because it's going to take less time to cancel out this force of gravity, than this force of gravity. This is exactly what happens when you drop a piece of paper. The piece of paper is fairly light, and the way it's shaped, it is very easy for it to reach terminal velocity, so it falls to the ground very slightly. If you take something heavier like a book, it's going to take a lot longer for it to reach terminal velocity. So you drop a book at a piece of paper, of course the book is going to hit the ground first when you include air resistance. If we didn't include air resistance, they would hit the ground at the same time. All right, one last problem. So here we go. Nellie Newton has a mass of 70 kilograms. If he falls, experiences 280 newtons of air resistance. What's his acceleration? All right, two arrows. Gravity, air resistance. Gravity is mass times gravity. Air resistance goes up. To get the net force, you subtract, divide, and done. Thank you. I hope this makes sense. I'm here for your questions. Let me know. Be well. Huzzah!